Hi everyone. So in this video, we're going to talk a little bit more about data formats and how we actually store information in files. Afterwards, we're also going to look at how this links back up to working with functions. And we're going to see how we can download more functions for Python from the internet that we can add into our programs to more easily work with all of these different formats of information. So to start us off, I want to think about images. When we think of an image, we usually think of some shapes, colors, space, an actual thing that we can see and think about. But computers, remember, have to store every single thing that they store and can show you as just numbers. So the way that this works is we have our image and we actually have to encode first some coordinates to talk about space. So we can think of this almost like putting a grid on top of the image. We'll have, instead of one whole picture, a bunch of tiny little squares that we can number on X and Y, almost like we were back in algebra class. So say we've got this picture of a tree right here. Instead of having green leaves up top and this little trunk down on the bottom, instead you can see we've got these boxes. And any one of these boxes I can easily refer to with numbers. Say this box here, if we were starting on the top left, would be 0, 0 for the 0 row, the 0 column. And then we would count up in either direction. So I could say, oh, this box of leaves here is 5, 3. And that gets us half of our equation here. Now we've got a way to talk about space in our image. If we want to add in how we talk about color, then we need some way to refer to any specific color. And you could say, oh, well, let's just number every color ever. But the problem with that is there are infinitely many colors. There's different shades of pink that are just a little bit off from each other. There's dark green and light green. So rather than trying to number and name every single color ever, instead, what we do to store image data is we pick a couple primary colors. We pick colors that when you mix them together can give you a wide variety of shades. And for light, that usually means us picking red, green, and blue. So if you've ever heard of RGB related to computers, that's what that's actually referring to, is our practice of mixing red and green and blue to get us any color ever. And numerically, what that means is in each one of these little boxes in our image, we're going to have first the numbers representing the position in X and a Y, and then we're going to have 3 more numbers representing an amount of red, an amount of green, and an amount of blue. And for some of these boxes here in our example image, that's really easy. This blue sky here, we might say, well, there's 0 red and 0 green and 100 blue. Same thing with our green leaves. Well, then there's 0 red and blue and 100 green. But the neat thing about this is it lets us express colors that don't look like red or green or blue at all. With our trunk here, that's a brown color, and brown is not really any of these. But it turns out if you mix a little bit of red and a little bit of green, you can end up with even colors as far away as brown. And so by mixing all of these numbers together, we can take something that is very visual and very far away from math, and on the computer express it in exactly the format that we talked about computers understanding and knowing how to store, which is just numbers. Each one of these little boxes is what's called a pixel, if you've ever heard of that. And in fact, even when your computer is talking to your monitor, all it is actually doing is transmitting these numbers And in your display, if you ever took a magnifying glass up to your phone or your monitor, especially if it's an older monitor with a lower resolution, you can actually see there is a grid of little tiny lights, microscopically small little red, green, and blue lights. And those numbers that your computer stores to actually display the image, it just tells it how much power should you send through those red and green and blue lights. So this numeric representation of images goes all the way not just to our storage devices, but all the way even to our monitors and our different displays. So that shows us just how versatile we can be in storing information in computers. Even extensions of this, things like movies, you can think of a movie as just a bunch of pictures, and so a lot of these same tricks will apply to let us represent that. So that shows us one example of ways we can store more abstract data, more complex information than just some of the variables we've been working with so far. The next example I want to look at is actually the one that CS110 has in the lab this week, which is how would we represent something like music? So music, it turns out, behaves much the same as our images, where we have to take the tricky part of this to represent and somehow map it back down to numbers. And in this case, if you've ever seen a piano, then you know that on a piano, we've got a bunch of different keys that each produce a different pitch. So we could already represent that as a number. Each one of those pitches is a little wave of energy floating through the air. But if we looked at those numbers are a little bit tricky. Like our middle C, the note that's in the middle of the piano, that would be 261.63 hertz. That's how fast the vibration is happening. And it would be really ugly to try to use numbers that specific when we were writing music on the computer. So what we actually do is, unlike with our images, there are not infinitely many numbers that we really use in music. Like we could, if we're getting into really modern music that's atonal, maybe you'll use every single frequency ever. But in our simplest representations, we actually can just number all of these keys and say, oh, well, that middle C, what if we gave that pitch, that sound, just the number 60? And then say, okay, well, the one after that, that black key right above it, that'll be 61 and 62, 63, 64. We can number the whole piano. And that gives us half of music. Music is pitch, but then there's also an element of time. Unlike a photo, music is happening over time and pitches will start and stop. So we're going to need a second dimension again. Just like how our pixels recorded both a place and a color, if we looked at the simplest music format, what's called a MIDI file, then what we will have is pitches and start and stop points. So a MIDI file will take a track of music, one instrument that's playing, and it will divide that up into time. And we'll say, okay, well, each beat of the song is going to be the next number up. And so I might say on this track, I've got note 75 starts on beat 1 and ends on beat 3. And a note at pitch 77 starts on beat 2 and ends on beat 4. And this will actually let me record almost in a similar way to sheet music, if you've ever seen that, where each pitch is starting and stopping. And again, this is just numbers. Like I could encode that entirely as numbers when I'm saving a file. And then when your computer is sending that data out to a speaker, it's going to receive those signals that tell it to vibrate at the correct speed to produce those pitches. And we end up with that music that we've written. So this shows us again, even a very, very complex piece of information, we can find a way to break that down and encode it in the one format that we know about, which is numbers on our computer. And so this is really powerful if you start thinking about information, not as we would perceive it as humans, but what is some way I can model it, capture it, describe it with numbers. Then as soon as you do that, you've converted it to a format where the computer can think about it. And if you take nothing else away from this video, that is the big theme that I want you to carry with you, is that as you progress further in computer science, a lot of what you do isn't learning new instructions for the computer. It's learning new ways to think about problems where you take something that is very human and convert it to something very mathematical, and then are able to convert it back and forth so that to you it represents the real thing, but to the computer it's in a way that it knows how to describe it and work with it. So those are our two examples of data formats. We could go on and talk about everything. We could talk about groups and how we assign people to groups and how that can be represented numerically. We could come up with a million examples. But the other thing I want to show you in this video is when we have one of these very complex formats, how do we actually work with it in our programs? And this is going to come back to what we talked about in the last video, which was functions. So we could, if we really wanted to, manually write these numbers into a file. We could write a MIDI file by opening up a hex editor program and just typing in numbers one after the next in the right format for music. We could do the same thing. We could create an image by manually specifying each pixel one at a time and what color it should be. But that's not convenient. It's not ergonomic. It would be easy to make a mistake. People have done that. If you look at early video game music composers, they literally had to write the numbers one after the other. But for us now, it would be much easier if we had a named instruction that could write those numbers in the right format for us. And then to use it, we would just use that name and give it whatever details were important for this. And when you hear that description, hopefully that sounds a lot like the functions that we were just working with before. Python comes with hundreds of functions that do a wide variety of things. Sadly, directly working with images and directly working with music is out of scope. Even in that giant library of functions we've got, there's nothing to work with every data format ever because there are too many. There are hundreds of different examples of very specific information we're holding for a very specific reason. So Python can't give it all of them to us all at once, but that doesn't mean we're out of luck. It turns out we're not just limited to modules that came packaged when we installed Python. There is this website that exists on the internet called the Python Package Index. And this package index is like a communal library of functions that other programs have written and published for us. Other programmers have gone onto this website and said, you know what? I've made a great set of functions for working with music. I'm going to call it MIDI util and put my name on it and put it out there. And then anyone else browsing the Python package index can say, oh, well, I want to work with MIDI. Let me search for MIDI. And then this package will come up and they can read it, review it, read some instructions on how to use the functions and what functions it gives you, and then pull it into their own program. And this is one of the coolest things to learn as a programmer, is that you don't have to solve every problem yourself, especially if it is a problem that has been solved again and again and again, often you can find some very helpful functions that do 80% of the work for you. And in our case, we're going to see how we can do that in just a minute. But that means we need to figure out, how do I actually download that package that someone else wrote and get it into my program? In Python, the way that we do this is with a tool called pip. So this tool pip runs on the command line, much like our Python interpreter does. So if we want to use it, what we do is we open up a terminal, and in our terminal, we're going to type pip install, and then the name of the package that we found on that package index in that library. And when we pip install whatever that package name is, this pip program goes out onto the internet, checks that repository of packages, and looks for one with the same name. If it manages to find one, it will download that into your computer's site packages folder. And then, once that happens, suddenly that new package name is a valid name for our import statements like we saw last video. So I wouldn't be able to just right now on my computer type import MIDI util and use those functions. But as soon as I run pip install MIDI util, it'll go and download those files, and it will put them somewhere that Python can find them. And then my import statement will work exactly like any of the others we looked at. Like I believe we looked at math random, the random package, and we could import those functions and suddenly they were there to use. In the same way, once we install, we can import any of those functions that this person has written for us, and they'll help us work with music files, writing them, reading them. So now the last thing I want to do is try actually writing one of these programs that works with a data format. So we're going to look specifically at that MIDI util package. So if I cut over to my text editor here, remember what I cannot do is, if I'm writing my new make song py Python script here, I cannot just import MIDI util directly. If I saved this and then I tried running my program right now, it's going to tell me there's no module named MIDI util. What this is not saying is that nothing like this could ever exist anywhere. All that this error is communicating to me is just that there's nothing called that downloaded to my computer yet. But remember, we had said I can pip install MIDI util, and then it will go and try to find something with that name. I run this, and it says, oh, well, I am installing MIDI util. I've installed version 1.2.1, and now that is included in my site packages. And now if I run that same exact program again, it's perfectly happy. So now we've seen how we download that. How do we actually use this thing? And it turns out we're going to use it pretty similarly to all of the other functions that we saw last video. So I'm going to change my import a little bit from MIDI util. There's one specific function I want. I want to import the MIDI file function. This MIDI file function is a function, so I'm going to put its name and put parentheses. And remember, we had said into here, inside these parentheses, I can put whatever arguments I want, whatever details about what I want it to do. In our case, for the MIDI file function, it only takes one argument, and that is, how many tracks does this music file have? So I'm going to say it has one track. We're going to keep it simple. And then this function, like most functions, is going to have a return value. And so this thing that it returns back is that song data. So if I actually want to save it, I'm going to put the whole function on the right side of an equals, and then I'm going to put the song here on the left. So now I've got that recorded, and from here I can actually start calling functions with this song to add notes to make music. And there are a couple little details that are slightly different from the other functions that we've worked with so far here. So a lot of Python packages like to organize their functions all around one variable and make it so it's easy that your program only stores one variable. And then once you've stored that one variable, you call the functions attached to it rather than calling them free floating. So what that would look like with our song, if I wanted to add, let's say, a tempo, a speed that the song plays at, there's an add tempo function. But instead of just being a free floating function that we call, instead I say, well, I'm adding the tempo to a particular song, and I'm going to do song dot add tempo. This is most common for functions that don't return anything, so that visually on the left we get a little bit of a better idea of what variable is related to this, what song is having a tempo added to it, in case we had more than one in our program that we were writing at the same time. So this is a technique called an object. The variable is an object, and this function is called a method on that object. You don't have to worry about that yet. We have a whole video coming up near the end of this whole sequence where we talk about objects and how we write them and how they're different. But for now, the only thing to keep in mind is that a lot of the time when we're using packages or we're using functions that work very closely with one particular variable, there's this other way that we will sometimes write them by putting a dot right to the left of our function name. So otherwise, this is going to work like any other function. We give it whatever parameters we want to set. And so for us, the tempo, we have to set a tempo on a track. So these tracks are numbered. So I'm going to put in a 0 for the track number. I have to put in when this tempo starts, what beat does it start on? So I'm going to put in starts on beat 0. And then I need what that tempo is, what the speed of the song will be. So I'm going to say, oh, well, maybe this starts at 150 beats per minute. So it's about a little less than every half a second. We'll hear another note if we're counting up by one. But now I've called this function, and this has added to my song information about the speed, which is all just numbers. If you look, all of our inputs to this function were just numbers. So it's much easier than us trying to edit the file directly, but we can still see how we're thinking about this music numerically as we write it. The same thing is going to be true with our notes. There's another function that this MIDI util package gives us where I can say song dot add note. And just like we had described when we were looking at music data as a data format, I'm going to need to provide a couple numbers to describe a sound. We're going to need a track and channel, so where this music is playing, which for us is going to be 0 and 0. And then we need all of that note information that we had described before, which is going to be where does this music start, what pitch is it at, and how long does it last? So for us, say I say, oh, well, I want note number 70. This third argument on add note is which numbered note do we want on a keyboard. So I'm going to start with 70, and I'm going to say, okay, well, this starts at beat 0. It starts at the very beginning. And I'm going to say it goes on for half a beat. So half is 0.5 in decimals. So I'm going to put a 0.5 there. And there's actually one other last argument we're going to need, one extra piece of information, which is how loud is it? So I'm going to put it's 100. It's maximum volume. And now that I've done that, I have all of the information needed to describe one single sound in my song that I'm writing. You can see there's a lot of numbers that go into just that one sound, and usually a song has hundreds or thousands of these sounds. So it's going to be very verbose to write it out. But every one of those notes, it's not hard to do. All I have to do is call that same function again, describe my next note, say, okay, well, it's playing on the same track, it's part of this same melody, but maybe my pitch is different. Maybe my next note, when I write this function call, it'll be note 68, and I want it to start right when the last one ends. So maybe it starts at 0.5, because if the last one was half a beat long, then this one has to start half a beat up. Maybe this one will be a full one, so I'll add a 1 here and say, oh, well, it's also max volume. One thing that can be helpful when you've got very dense function calls like this, if you notice, this is a lot of numbers that are all easy to mix up and forget which one means what. It can be helpful to create variables for yourself just to store these things so you know what they are, especially if they're ones that get used over and over and over again. So in my program, maybe I could say, oh, well, I want to remember what these 2 zeros are in the beginning because they mean different things. Maybe I should create a track number variable and say, okay, well, I'm dealing with track number 0 right now. And then everywhere that I called that 0 and I was talking about the track, I can instead put in that variable to remind myself what that 0 was for. I could do the same thing, say, oh, my channel number, that is what this second 0 was. So let me replace that with a channel number here. That 100, that is the volume. So maybe my song has a volume that's going to be consistent throughout. Let me just remember that that's what that last number is. And now this looks a little bit longer. These lines are a little bit more dense, but I've got a better idea of what each one of these parameters is for. And the only ones that are numeric are just the ones that are constantly changing. Even these, if I wanted to, I could say, oh, well, I'm a musically trained person. I don't deal with numbers. I deal with note names. You could even go through if you wanted to and say, okay, well, high C is going to be 70 and high B flat will be 68, whatever names you want to give them, and then you could use those. Or if you just want to deal with pitches, you can keep them completely numeric if you'd prefer. But we could go through and add these notes one after the next. But normally early on when I'm writing a more complicated program, one thing I like to be able to do is immediately start testing that I'm on the right track. Instead of spending a half hour writing this out, doing napkin math to figure out what numbers go in here, what pitches, what lengths, and what beat will they be on. Instead of trying to do that all in my head and just test it once at the end, I like to find ways to test along the way. And so what I'm going to do is before I write any more music, I'm going to use 2 more functions that let me actually convert this to a file. So the first of these is the open function. The open function actually comes with Python. It's not part of MIDI util at all. But open lets us take a file name and create a file there. So I'm going to create song.mid, the name for these MIDI, very simplistic musical files. It's not as complex as an MP3, but that's what lets us write it by hand. And I'm going to say I'm going to open this in writing mode. So I put this little WB here as a second parameter to open. And what this open function will return to me is a file, the actual file that I'm writing. So you can see, even if I don't have this file here in my make song, I say, okay, open this, create this file, and then song, write yourself to file at this file location. So this one is a MIDI util function, much like our add note and our add tempo. I'm going to write this into the file. And now, when I run my Python program, watch the files that are in my week 6 folder here. I run it. Nothing plays audibly. I can't hear it. But when I refresh, suddenly there is this song file that's here. And if I open this up, I can't really tell what's going on. This looks like garbled text to me, but it looks like garbled text because it's actually just those packed together numbers. And now, if I actually try playing this in a music player, what I do, you can hear the notes play, those two notes that we wrote. The first one and the second one. And if I now go and say I added in, painstakingly mapped out a bunch more notes, I could end up with an entire song. Say, oh, well, add a note, this one, then this one, then this one. Each time figuring out where does it start, how long does it last, and what pitch is it at. Then when I run my program and generate this new song file, we can end up with music. And so that shows us right there how we can start working with more complex data in our programs. You can see no matter how complicated the problem becomes, ultimately, a lot of what our programs are going to be doing is just finding the right tools that have been built for us and then calling the right functions to describe whatever information we've got as numbers, because numbers are what computers are really good at working with, or even as text, because text is a really easy numeric translation, and then we can have a bunch of tools dealing with text. But that is what a lot of our programs, your entire programming career are going to be built around, is finding the right function and then finding the right representation of your data. So this has been our exploration of data formats. Try this, download this, start playing with it, because playing is the best way to learn this type of programming. And from here, we're going to start looking at other interesting ways we can steer our programs and create different sets of instructions for different situations. So look forward to that, and I'll catch you all in the next video.